right, books open to page 126. You had questions 3 through 6 for homework last night. Also did number 6 on page 118. Practicing with the law of heat exchange. Well, let's take a look at these together. Obviously, numbers 5 and 6. They're on page 126. A little bit more thinking questions. So curious to see how we did on these. And question number 3, what is vapor pressure and how does it relate to the boiling point? What did you have for this, Olivia?
Vapor pressure is the partial pressure at which the liquid and vapor phases are in equilibrium.
Good.
I know my other one's wrong.
Uh-oh. Can you help her on the second half? Because she has no...
A substance's boiling point is... okay, so the vapor pressure equals the total pressure of all the gases present.
At the boiling point. Okay, back to recover. We'll give it to you. All right, so where the gas phase and the liquid phase are at equilibrium, in other words, evaporation, condensation are at equilibrium, they're evaporating, condensing at the same rate, that's the partial pressure, that's called vapor pressure. Boiling point is whenever the vapor pressure equals atmospheric pressure. Number 4, what is a phase diagram and why is it useful? Very subjective question there. What did you have, Grace?
Phase diagram is a graph that shows the phase or state of a substance at different pressures and temperatures.
Good. And why is it useful?
It's useful because it represents the phases.
The relationships between the phases. You can see the relationships between the different states of matter, different phases of matter. Good. Number 5, good thinking question. A pot of water on a stove is boiling slowly. What will happen to the temperature of the water if the stove burner is turned up higher, which of course causes the water to boil more rapidly? But what happens to the temperature of the water? Olivia?
It increases.
No. So, Grace?
The temperature will start heating faster.
Well, temperature doesn't heat. Temperature could increase, decrease, or stay the same.
Start heating faster.
The water will absorb more heat, but will it increase the temperature? No. You turn it up more, it goes up to 100 degrees Celsius. It doesn't get hotter than that. It gets to 100 degrees Celsius. It will boil faster as more heat's added, but it won't actually increase temperature. Remember yesterday we talked about latent heats of fusion and vaporization. So once you get to that boiling point for water, that is its max temperature. After that, it can only increase temperature once it's converted to the next state of matter. So no, turning it up doesn't actually increase the temperature once it's already boiling. Now, until it's boiling, yes, the temperature can increase and increase and increase. But once it hits boiling point, that's where it stops. And then from there, it's just a matter of turning it all into a gas. Number 6, another thinking question. Why can a given mass of steam at 100 degrees Celsius burn your skin more severely than the same mass of liquid water at 100 degrees Celsius? We'll start with Grace this time.
The steam will burn more because the energy will become, the energy will be higher in the steam than the water. Because when water turns to steam, it releases more energy.
It absorbs more energy. Absorbs more energy. There we go. Steam has more energy because that latent heat of vaporization has been added to the water molecules. Now, I would argue this. Are you really going to get the same mass of steam as you would of liquid water? For instance, let's just say you had 5 grams of water. That's not a lot, but 5 grams of steam would be a much larger, like more space amount. How would you get 5 grams of steam to hit the same spot? So it's a little unrealistic, but the point is steam has more energy at the same temperature than water does. That's why it's a gas instead of a liquid. It kind of goes back to the gases always have more energy than liquids. Therefore, the burn would hurt worse. All right, flipping back to page 118, let's be reviewing a few things as we're turning back. We said that, what is heat? What is heat? Tyler?
It is the transferring of energy.
It's the transferring of what kind of energy?
Thermal energy.
Thermal energy, or you could say internal energy, but it's that flow of internal thermal energy. Heat always flows in which direction, Abigail? Out? Not necessarily, not for an ice cube. It flows in on an ice cube.
From heat to cold.
From hot to cold, there we go. Always flows from hot to cold. And the heat will flow until 2 objects have the same temperature. If they have the same temperature, no heat flows because there is no hot and cold. That point is called what, Grace?
Thermal equilibrium.
Thermal equilibrium. We said that every substance heats a little bit differently. Some substances heat very quickly, other substances heat slowly, meaning some substances need to absorb a lot more heat for their temperatures to go up. What term describes the amount of heat required to raise just 1 gram of a substance 1 degree Celsius? The heat required to raise 1 gram of a substance 1 degree Celsius. Olivia? It's that substance's specific heat. And every different substance has its own specific heat because every substance, you have a gram of it, you want to raise its temperature degrees Celsius, it'll take a little bit different amount. The heat equation is based off of this idea of specific heat. What is our basic heat equation, Tyler?
C squared plus and delta T.
There we go. Q for heat is equal to the specific heat times the mass times the change in temperature. We said for our purposes, heat will be measured class in joules, though we're going to have large numbers of joules sometimes, so we may change it to kilojoules, but the default is going to be joules, really because of the way specific heat's defined in our textbook. Different textbooks may define specific heat in different units, but our book uses what units for specific heat? Volunteer, they're kind of weird. Weird units. Tyler wants to?
Is it joules over grams times temperature? Final temperature?
Degrees Celsius being, since we're dealing with units, that would be the units of temperature. And that reminds us, class, that mass has to be in grams and temperature change in degrees Celsius. Remember, temperature change is always what minus what, class? Careful. Try that again. Temperature change is always what, class?
Final minus initial.
There we go. Final minus initial. So whatever it ends up at minus what it started at, which means if the temperature is going up, then delta T, class, would be positive. And if the temperature goes down, then delta T would end up being negative. Mass is always positive, specific heat is always positive, so the delta T is going to determine the sign of the heat. Negative change in temperature, negative heat, meaning heat has been lost or released by the system. If delta T is positive, then it means heat has been absorbed or gained by the system. There we go, good. We said that we can measure heat in an insulated device. What is that insulated device used for measuring heat, Grace?
Calorimeter.
A calorimeter. And the calorimeter is based on the law of heat exchange, which is based on the first law of thermodynamics. But what is that basic law of heat exchange? Olivia?
Heat lost equals heat gained.
There we go. Heat lost by one thing equals heat gained by the other thing once they get to equilibrium. Though we'll make one small edit here. On which side? The loss side. We'll say negative Q lost equals Q gained, and in for the Q, of course, CSPM delta T would get plugged in. And that's the formula we needed to use on page 118, number 6. Abigail, you had the homework pass, so didn't do it. That's fine. Would you read number 6 for us, though, as the rest of us get ready to check our work?
A 24.1 gram sample of zinc is heated to 99.4 degrees Celsius and placed in a calorimeter containing 60 grams of water at 23 degrees Celsius. The final temperature is 25.8 degrees Celsius. Calculate zinc's specific heat from the scale.
All right. Is the zinc hot or cold, class? Hot, really hot. Okay, presumably over a burner, it's heated to almost the boiling point of water, right? So that would burn your skin hot. I don't know. I'm trying to wonder, would it melt first? Anyway, but it's heated up really hot, and then once it's nice and hot, it drops into a cup of water. The water's room temp, okay? What's going to happen, just plain English, what's going to happen to the zinc, class? It's going to cool down. Scientifically, we'd say it's going to lose heat. What's going to happen to the water? It's going to warm up. Scientifically speaking, it would. So my suggestion, you don't have to do this, is to go ahead and write what's what. I'm going to put the zinc on the loss side, the water on the gain side. So as I plug in my values, I see what I've got going on. In each case, CSPM delta T. Of course, this leading with the negative. Here, CSPM delta T. Do we know the specific heat of zinc? Even if we did, it's based on this data specifically, so we may be a little bit off depending on, but we're going to do the calculations anyway. we're finding the specific heat. The mass of the zinc. Well, it says the mass was what, Abigail? 24.1 grams. And then for the temperature change. Well, before we dropped that really hot piece of zinc into the water, it was at what really high temperature, class? 99.4 degrees Celsius. But then we drop it into the water and it loses heat. It cools down until eventually, what is the temperature of the zinc? Now, it says that's the final temperature, but it doesn't tell us whether that's final for zinc or water. Thoughts, Olivia? It'll be at equilibrium, so it'll be both, right? So when it says the final temperature is 25.8, is that zinc or water? Yes, it's both of them, all right? Because they'll be at equilibrium when everything's said and done. So when we subtract there, what is that delta T, Grace?
Negative 73.6.
Good, negative 73.6 degrees Celsius. And then coming over here to the water, we might have its specific heat memorized by now. I don't know, we've used it a bunch. 4.18. Joules per gram times degrees Celsius. The mass of the water. How much water was in the cup, Abigail?
24. Wait.
That was the
60
zinc.
grams.
There you go, 60 grams of water. And the delta T. Well, again, final minus initial. Well, final, we already said is going to be 25.8 for both of them. What was the water at before the zinc was plumped into it?
23.
There we go. It says the water was at 23, so that was initially 23 degrees Celsius. The delta T here, much smaller, class. Just 2.8 degrees Celsius increase. At this point, it's just a lot of numbers in the calculator. All these get multiplied together. If you wanted to, you could get one number, write it down. You could cancel the two negatives, because negative times negative is positive. If you wanted, you could multiply these together, and then divide whatever number you had over there by whatever number you have here. Or, if you really want to do it on the calculator, this times this, divide away that number, then also divide away that number, since they would both end up being going down there. We end up getting what for the specific heat of the zinc? Grace?
0.39590.
Blah, blah, blah. Okay, let's round to sig figs. I'm seeing 3, 3, 3, 3, and 3. So let's round to
0.396.
and then specific heat. Do you remember the units?
Joules over grams times degrees Celsius.
There we go. How many have this answer? The 0.396 joules times, okay. Abigail, questions on it. You didn't do it, but you feel good about it?
Yeah.
All right, Tyler, question.
No idea what I did. I'm up by the wrong heat.
Ah, gotcha. Okay. Questions at all? Yes, ma'am.
You just add the other side and then divide.
We'll
by
multiply. You multiply these two together to get whatever number it is. You're going to multiply all this number to get an even bigger number. Actually, no, this would be a smaller number, wouldn't it? Anyway, you get a number over here, you get a number over here with the C sub SP. Divide whatever number's over here from that side, and that's where you'll get that number.
So divide that side by itself and then that number.
Right, because you're dividing to cancel. Divide to cancel what you do. Just like if we had like a 3x equals 12, we say divide both sides by 3. That's just to get rid of the 3, so we have x by itself. Same way, we want the C sub SP by itself. Good. All right, other questions on law of heat exchange? Questions on law of heat exchange? And then yesterday we began looking at a new type of heat. The book also refers to it as enthalpy. Same idea, but heat that's added to a solid to turn it into a liquid. Plain English, what do we call it when we turn a solid into a liquid, class? It's called melting, right? Well, when we melt something, the temperature doesn't change. Once the object gets to its... An object doesn't melt just whenever. You have to first raise the temperature to its melting point, right? So once you get an object to the melting point, well, it's still a solid. If you wait long enough, it'll turn into a liquid. What's happening in that wait long enough? You're adding more heat. The temperature's not changing, you're just adding more heat. And as more heat adds to that solid, it breaks down that cohesive bond between the molecules, turns it into a liquid. What do we call the heat that must be added to a solid to turn it into a liquid? It doesn't change the temperature, but it changes it to a new state of matter. What do we call that heat? Had a special name.
So it's not latent heat.
I'm sorry?
It's not latent.
Latent heat. It's referred to as latent heat. Latent having the idea of it's there, but you don't really think about it because the temperature is not changing. Specifically, if you're melting something, we said it's called the latent heat of...
Vaporization. Condensation.
No,
Vaporization.
not vapor. We're melting something. We're not vaporizing it. Melting something. What's that physics word that means melting? Okay, look it up in the notes real quick. That's okay. Look it up in the notes real quick. Latent heat of... She found it, fusion. All right, so the latent heat of fusion. It doesn't change the temperature. Once the thing is at, if you want to change its temperature, there's your formula, right? But once you get it to the melting point, you would add latent heat of fusion to it, notated L sub FUS. The book uses this notation for enthalpy of fusion. Means the same thing. I'm lazy, I like this. And it's one of the reasons I do it, laziness. But add the latent heat of fusion, it just is a certain number of joules that every gram needs. You multiply whatever the mass is times that many joules per gram. That would tell you how much heat would be needed at the melting point to melt the thing. We said if you have a liquid and you're turning it into a gas, plain English, back when you were in elementary school, what do we call it when a liquid turns into a gas? Class? Evaporation. We'll use a similar term called vaporization, right? For turning that liquid into gas. But we said that a liquid reaches a certain point that it cannot get any hotter. That's its boiling point. At that point, the liquid stops heating up and it begins changing from a liquid into a gas. Molecules get more and more and more energy till they just fly away from the liquid. They have no more cohesion left between the molecules. They have too much energy for that, and away they fly into the air as a gas. The heat that has to be added at the boiling point to cause molecules of a liquid to become molecules of a gas is called the latent heat of class vaporization. That one's a little bit easier to remember, I would think, right? Evaporate, vaporization. So latent heat of vaporization, I think, will be easier. It's just the fusion one. Vaporization, okay, is the harder one to remember because we don't think of fusion and melting necessarily in the same sense. Frankly, fusion's not a word we use a whole lot anyway. But the latent heat of vaporization, heat that has to be added to a liquid at the boiling point to actually evaporate or vaporize everything. Now, we could, rather than adding heat to a solid and melting it, we could take a liquid and suck heat out of it until it turns into a solid. Usually we would refer to that class as what? Think of putting water into a box and it turns into ice. We call that freezing, right? Normally we think of it as freezing. Well, in some cases, like if you had molten zinc, right? We have the melted zinc and we let it cool just a little bit. It doesn't take long before it hardens again. We didn't actually freeze it. So the opposite of fusion isn't necessarily freezing, though we could think of it that way. And remember the technical term for it? The opposite or the inverse of fusion? That is an opposite, but it's not this one. It does start with a C.
Crystallization.
Heat of crystallization, negative heat of fusion is how I'm just going to think of it, rather than remembering heat of crystallization. That is technically the term, but it's just negative heat of fusion, because you're going the opposite direction. Instead of adding heat, you're taking heat out of it. You're taking energy out of the liquid, which the more energy that comes out, slower and slower the molecules move, the more and more cohesion they'll have. They freeze, in a sense. They form into a solid. What about the opposite of vaporization? Instead of a liquid turning into a gas, gas loses energy. It cools. It becomes droplets, becomes liquid. There's your turn. That's condensation, right? Well, negative vaporization is going to be the same as condensation. You take out this many joules of energy from a gas, and it will turn into a liquid. That's the idea behind liquid nitrogen or these liquid gases, is they just simply get the temperature so incredibly low, they take away more and more heat from the liquid that it finally, from the gas rather, that it has to condense into a liquid. And of course it's not real stable, but you've got your supercooled gas in liquid state. And so we said that if we want a temperature change, of course we have this equation, but if we had a state change, we're going to use one of those. I mentioned it a second ago, our equation is pretty straightforward. Q equals class. We don't need specific heat. M times L. Whichever one it is. Subnotate fusion, vaporization. I'll put a little line there, doesn't really matter. But mass times latent heat. Whatever the latent heat is, times the mass. Lots of mass, lots of heat. A little bit of mass, not as much heat. That's what we would use anytime for a state change. This is what we use anytime we have a temperature change. And this is where we left off yesterday. So that should kind of catch us back up. Questions on what we were covering yesterday. We feel like, okay, yep, mind refreshed, we're ready to roll. Then turn in your books, if you would, to page 121. I want to pick up on page 121 where we were yesterday. We did the first example problem at the end of the hour. Page 121, example 6.4a, and read the example problem at the top of the page for us again, just to refresh our memory on what we've been talking about. Tyler?
How much heat is needed to warm 25 grams of ice at negative 15 degrees Celsius to 25 degrees Celsius?
All right, so we might remember this. We have 25, it was 25 grams? All right, and we have ice at negative 15 degrees Celsius. That's your usual temperature for the freezer in your house. So you take an ice cube, let's just suppose it's a 25 gram ice cube. When it's in the freezer, it is probably right about negative 15 degrees Celsius. That's a pretty realistic temperature. And we said we can't take ice at negative 15 and turn it into ice at 25, because ice doesn't exist at 25 degrees Celsius. Where does ice stop being ice, class? At 0. So we said what we've got to do first of all is get it to ice at 0 degrees Celsius. And if you're looking in your textbook, we see that here. It lists here the first thing in this second, see how there's kind of a line in the middle of the box? Right here it shows that the heat of ice is 2.10 joules per gram times degrees Celsius. That's a specific heat. 25 grams, and we need to bump the temperature up 15 degrees. And we found that to do that, it was 787.5 joules of heat to get it to the melting point. Now, once something is at its melting point, it doesn't instantly melt. It doesn't just magically become liquid. No, you keep adding more heat, class. We add what? Specifically called the heat of fusion, the latent heat of fusion. That's what needs to be added to take ice at 0 degrees and turn it into water at 0 degrees. That's the state change. That's where we're going to take the mass, which is the 25 grams, times the latent heat of fusion. You see that as the second line here. They have Q sub FUS, mass times, and again, they use the delta FUSH notation, 25 grams times 334 joules per gram. That gets us to 8,350 joules. Now, our negative 15 degree ice has turned into 0 degree water. However, look at the bottom problem, the second problem on this page. It builds on this first one in a way. Look at example 6.4b. Read that for us if you would now. Olivia?
Calculate the heat.
Right under example 6.4b.
How much heat is needed to warm 25 grams of ice at negative 15 degrees Celsius to 110 degrees Celsius?
All right, now we've already done the first two steps, so I didn't want to have to redo those steps. But now they're greedy. They don't want 25 degrees Celsius room temperature water. You know, the kind of water when you pick it up off the table and take a drink, it's like, ew, that's not very good. That's not very refreshing, right? Not room temperature water. Now we want it to turn into 110 degrees Celsius. Well, class, does water exist at 110 degrees Celsius? No, at 110 degrees Celsius, we must be talking about steam, right? We're talking about steam. So, for instance, this would be like if you had your pressure cooker, right? Your Instant Pot. Okay, you put the ice cube in the Instant Pot and turn it on. Well, the ice is going to break down and slowly gain energy until it gets to your melting point. Then it'll all melt till it gets here, and then the temperature will start climbing again. Your 0 degree water will keep going, getting hotter and hotter until finally water will reach what temperature in your Instant Pot? Presume, not 110. It only goes as high as what? What's the hottest the water gets? 100 degrees. Water's going to get up to 100 degrees Celsius, and then a strange thing happens at 100 degrees Celsius. It starts actually evaporating, correct? So we've got this. Well, is this a phase change or a temperature change, class? It's a temperature change. So we need the formula Q equals CSP M delta T. Now we're dealing with liquid water. In the previous problem we had ice, so we used 2.10 joules per gram times degrees Celsius. But liquid water has the specific heat we've memorized, class. 4.18. The mass is still 25 grams. It's just not an ice cube anymore. It's a little tiny puddle in the Instant Pot. And we need to raise the temperature how much? From 0 to 100, that's a change of 100 degrees, right? 100 degrees Celsius increase in temperature. Let's multiply these three numbers together and see how much heat it takes to get water at the melting point up to water at the boiling point. That's a good size number. How about when you got it? 10,450 joules to get the water up to the boiling point. Now, does the water immediately boil as soon as it hits 100 degrees? No. No one ever has been boiling, turning on their pot of water, watching the temperature go up, and as soon as it gets to the boiling point, poof, all the water evaporates instantly. It takes more and more heat, continually adding heat to get that water to actually boil. Once it's all boiled, your water is no longer water, it is now steam, but it's still at 100 degrees Celsius, right? That conversion of water at 100 degrees to steam at 100 degrees, liquid to gas at the boiling point, that's called latent heat of vaporization. So that's where we're going to go back to this equation. The mass times the latent heat of vaporization. Well, we know how much mass we have, class. It's still 25 grams. But look at your chart on page 120, right across the page. Looking at water, notice the boiling point. Now it's listed as 373 Kelvin. That's 100 degrees Celsius. But notice the heat of vaporization. How many joules per gram of water does it take? And this is why it takes water so long to boil. So we're going to take 25 grams times 2,260 joules per gram. That's a lot of heat. That's a lot of latent heat of vaporization. How much does it take to actually evaporate all 25 grams of water that used to be ice?
56,000.
Anyone else get the same number, 56.5? We like that number, 56.5 joules. Now we've got steam. But this particular problem, just to be annoying, they're not content with simply having steam. How hot do they want the steam, class? 110 degrees. And we've already got 100 degrees steam. Now we need to get it up to 110 degrees Celsius steam. Do we see that? Now is this a state change or a temperature change? Steam at 100 to steam at 110. That's a temperature change. Back to what equation, class? CSPM delta T again, right? Now, steam does not have the same specific heat as water. So we've got to look back, specific heat. Turn all the way back to page 116, and it lists all your specific heats. What is steam's specific heat from page 116, toward the bottom of the chart?
2.08.
2.08 joules per gram times degrees Celsius. Now, our 25 grams, remember ice cube? Nice little ice cube, little puddle. But as steam, it's going to be sort of this cloud you really can't see, right? It's in the instant, but it's just in a cloud form, so to speak. But we still have 25 grams of it, correct? It hasn't gone anywhere. And the temperature change, trying to get it from 100 degrees steam to 110 degrees steam. 10 degrees. And so we multiply. And it's up around 500. How much heat does it take to get the steam up 10 degrees? Anyone else get 520 joules? We like that number. Okay, so here's the question. How much heat, this is what the problem asks that Olivia read for us. How much heat is needed to warm 25 degrees of ice at negative 15 Celsius to 110 degrees Celsius? Well, this much to get to the melting point, this much to melt it, this much to get to the boiling point, this much to boil it, and this much to superheat the steam. So what do we do with all 5 of those numbers? Aren't you thankful for calculators? Punch them in, start typing. We got to add all 5 of these individual heat numbers to get the total heat needed for this problem. And I'm going to guess somewhere around 75,000. How much? 79, 270. Anyone else get 79, 270?
I got 76.
Uh-oh. We got a 76er over here.
76.5.
Ooh, 7687.5. Okay, so I've got 2 different numbers. Oh, she rounded for something, okay.
766,007.5.
76607.5? Is that what she's?
76,687.
I'm a little off. I think I just added something else on.
All right, you got the tiebreaker here. She bowed out, so we got these two.
But now I have
Oh, yeah,
79,200.
Wait,
I forgot to add the 520.
Forgot to add the 520, he says.
I got 76,607.
76,607 point. Yes, you said the same thing?
76,607.5.
All right, let's roll with that. We got 3 people agreeing on it. We can't all be wrong the exact same way, surely. 76,607.5 is what we're going to settle on. Let's see what the book says. Yes, book agrees. 76,600 rounded, so that would be this number then. 76,600 joules of heat, just for a little ice cube. Just to turn that little ice cube into a little cloud of steam. That's how much heat it takes. Question for you. What if we had a little cloud of 25 grams of steam floating in the air, and we wanted to condense it into liquid water and cool it down and put it in the freezer and freeze it into an ice cube? How much heat would that take? Negative 76,600 joules. That's how much energy or heat would have to be lost to reverse that process. That make sense? So since it's getting hotter, since it's gaining energy, it's positive. If the same problem started with steam and went to ice cube, well, that would be reversed. So it would be negative. But this process would not change. Questions on this idea of state changes, latent heats? Questions on that? Sort of, yes, no? All right. We don't have a lot of time. Let's look at one more problem. We'll have to finish up tomorrow. Page 122. Page 122. And let's see. We only have time for one problem. So, Grace, you missed all of last week. I'll let you pick. 1, 2, or 3. Pick a number. 1, 2, or 3.
2.
Problem 2, right in the middle. All right, read problem number 2 for us, Grace.
23.5 gram sample of liquid lead is at its melting point. How much heat must be removed to cool it to 25 degrees Celsius?
All right, so we have, what did it say we have?
Lead.
What state though?
Liquid.
We have liquid lead. Now, class, is lead normally a liquid? No. That means that it has already been melted, correct? We've already melted all of this lead. We're in some kind of furnace or something, or the lead is, we're not. The lead is in some kind of furnace. It is already melted, but it says that the lead is at its melting point. It's just at its melting point. In other words, it's at the right temperature to melt, and it's already been melted, but it hasn't been heated anymore. Does that make sense? So it hasn't started gaining any temperature. Well, begs the question, what is lead's melting point? Great question. Flip back to page 120. 600 Celsius? 601 Celsius. Yes, 601. Oh, 601 Kelvin. All right, it's at 601 Kelvin. What do we have to do to make it Celsius? Now add, remember Kelvin's always the big guy. Minus, and let's forget the 0.15, shall we? Let's make life easy on ourselves. So subtract 273. The 0.15 doesn't make that much of a difference. What do we get?
328.
So it's at 328 degrees Celsius. It's already at the correct temperature. We want to turn liquid lead into what state? Solid lead. Now, if we go from solid to liquid, that's called melting, or the physics word is fusion, right? But from liquid to solid, that would be crystallization, or more practically speaking, negative fusion, right? We're not technically freezing the lead, but negative fusion, right? So this here, it's not going to change the temperature, because it's right at the correct temperature to melt or crystallize, right? Make those solid. It seems weird to say crystallize because lead isn't crystals. But anyway, I digress. To go from liquid to solid, it's the heat of fusion, but it's going to be negative heat of fusion. What do we do with the heat of fusion? Then we multiply it by the mass. Remember, that gives us the total heat needed. So how many grams of liquid lead was it again, Grace?
23.5.
Random number. All right, so 23.5 grams of liquid lead. So we're going to take the 23.5 grams, and then flipping back to page 120 again, the heat of fusion for lead. Good, 24.6, but remember, we're going the other direction. We're not adding this heat, we're taking this heat out of the liquid lead so it will go back into a solid. So negative 24.6. We said the mass was 23.5 grams. So how much heat does it take us to suck out of the liquid lead, to absorb out of the liquid lead so that it will go back to being solid lead again? Not degrees, but joules. All right. Anyone else get negative 578.1 joules? All right. So that gets it back to a solid, but they wanted it to cool all the way down to room temperature so we could touch it. They want us to cool it all the way down to 25 degrees Celsius. Now it's already a solid, so that part's good. But you see, we want to take our solid lead that's still really hot, right there at that rather volatile melting point, and drop it all the way down to nice, easy room temp. This is not a state change, is it? It's a temperature change. So we need what formula for Q?
CSV and delta T.
All right, so the specific heat of lead, what page was that on? That was like several pages ago. Specific heat of lead, page 116. Lead's specific heat, 0.129. All right, the mass is still 23.5 grams. Now here's the fun one. What's the temperature change? Remember, final minus initial. I need to get it down to 25 degrees Celsius. It's currently 328. Negative 303 degrees Celsius. Negative temperature change because negative heat. We're taking the heat out of the lead. And so we multiply all those numbers together, and we get a slightly bigger value here, I think. Anyone else get negative 918.5 blah, blah, blah? Getting some nods there? Negative 918, got a weird look from somebody else though. Negative 918? Cheat and look at my own. Yes, negative 918.54 is what I had also. So that much heat actually melts it, because it was already at the melting point very conveniently. This much heat removed, takes it down to room temperature. So how much heat must be removed from the liquid lead at the melting point to get it down to room temperature as a solid lead? Class, what do we do? Add the two amounts together. Negative 578.1, negative 19.5, blah, 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 ends up giving us
negative 1,496.6445.
All right, how many sig figs in this problem? 3, 3.
I didn't.
So we got negative 578 plus a negative 918.5.
Oh, negative.
Remember, they're both negatives, so we're going to add and keep the sign, going back to our algebra days. If both the signs are the same, add, keep the sign. So negative 1496, I think is it 3 sig figs?
Yes.
I'm seeing 3, so let's cut it off here. Oh man, that's going to be scientific notation then. Because this was what it would round to, right? So negative 1.50 kilojoules. There we go. Let's dodge it that way. If we write kilojoules instead of joules, put a dot here instead of a comma, and then we just show 10 for the 3 sig figs. Or negative 1.50 E3 joules. Questions on this? Do we feel like we've got a little better understanding after today of how the whole latent heat thing works? Okay? Get it to the right point. Get it either to melting point or boiling point by doing a temperature change. At that point, then go ahead and actually melt, boil, condense, crystallize, whatever the substance. Questions? All right, there is no homework this evening. However, I do have an extra credit for you if you want to tackle it, because we're going to look at it tomorrow. If you don't do it, no problem. If you do it, get a few extra points on your test coming up on Tuesday. Page 126, number 7D. Page 126, number 7D will be your extra credit. Abigail, quick question?
Yeah. How'd you go from 1,496.6?
Well, the 6 bump this up to a 10, which bumps this up to a 5. And of course we keep the 0 because it's before the decimal.
But you got 1.5.
Oh, kilojoules. Sorry, this is joules. So negative 1,500 joules. I'm like, oh, that's so annoying. So I said, well, if we go kilojoules, then the comma gets replaced by a decimal because kilo means 1,000.
Where'd you get? Oh.
I just went to thousands of joules instead of individual joules.
Oh, okay, that makes sense.
All right, have a wonderful day.